Hello students. In this second video, we're going to derive the equation of an ellipse in a slightly different way. So first of all, let's examine the property of an ellipse. I think just from our kind of everyday experience, you know that the ellipse has an axis of symmetry. In fact, it has two axes of symmetry, right? It's symmetric vertically and also is symmetric horizontally. And now that we know the ellipse has a property whereby the distance between any point on the ellipse and the focal point, let's call that D1, and the distance between that to a directrix line D2, that D1 has to be less than D2. Okay, that's what makes an ellipse. And as you trace out the point P all along, okay, all along here, it's going to eventually come back, loop around, okay, and then repeats itself. Well, if it's symmetric, wouldn't it make sense that there is another focal point over here and another line of directrix such that the distance, let's call that D1 prime, and let's call this D2 prime, would have the same ratio and the same relationship? So D1 prime and D2 prime should be the same as, in blue now, D1 over D2, right? Should have the same relationship, right? And we call that ratio R. So by arguing symmetry, we know that there must be another focal point, and we know that there must be another line of directrix. And that's going to lead us to a very important property. So I'm going to redraw my diagram in the following way. I'm going to draw my D1 prime as the same point P that is going to the second focus now, and D2 prime is the distance from the point P to the other directrix. Okay? So D1 prime divided by D2 prime, again, because it's the same ellipse, therefore it must have the same ratio R, right? So let's call that ratio R. All right? Now let's do some simple calculation. D1 prime must then be equal to R times D2 prime, and D1 must be R times D2. Another thing we notice that I'm going to highlight in orange is this distance here must be a constant, right? Because obviously the line of directrix don't change. So therefore, I also know a relationship D2 plus D2 prime equal to a constant. Let's just call that K. Well, that leads to a very interesting conclusion. Well, let's add these two equations, right? So D1 plus D1 prime is equal to R times D2 prime plus R times D2. I can factor out the R, D2 prime plus D2. But we said D2 prime plus D2 is a constant. So this is equal to R times K. Okay? Well, R is also a constant because we said for a particular ellipse, we're going to fix a certain ratio, R that is less than 1. So R times K itself is also a constant. Well, D1 is the distance between the point P to the first focus. Let's call that F1. And D1 prime is the distance from a point P on the ellipse to the second focus, the F2. Which means that for any point P, the distance, called the focal distance, to F1 plus the focal distance to F2 is a constant. Okay, so what it means is that an ellipse has this very interesting property that for any given point P on the ellipse, its focal distance to the first focal point plus the focal distance to the second focal point, if you add them together, it's always going to be equal to a constant. And this allows us to derive the equation for an ellipse in a slightly different way. So at this point, I'm going to refer you to the textbook at section 10.3, starting at page 665. There's a very well done derivation of how to derive the equation of an ellipse using this property. So go ahead and read that in the textbook before you start on the third video.